Okay, I have a brief board recording, and hopefully the video will this one I want to keep. Well, I guess we'll find out. What the heck it does. Okay, final chapter 10.
10.
Yeah, chapter 10. Root finding. So we'll cover half a chapter. Let's see. Well, actually, yeah, much of a chapter this week, and then I'll take a look at the schedule to make sure I'm remembering. Okay, so that's today. Okay. So yeah, so the week after Thanksgiving is when the rest of it will be covered. So half this week, half during the last week of classes. Well, someone tells me that I have on the Tuesday after Thanksgiving Newton's method, and the Thursday after Seeker method. I feel it's all that 28. We'll see. So I've had a practice final exam solution posted all semester long. I do need to check that because I had to make changes to the midterm compared to when I last talked about 2021. And what's posted there now for final should be pretty close to being on the mark, but I'll also have to take a quick look at it. Okay. All right. So we've been studying some fundamental problems this semester. You know, how do we find a polynomial that passes through select points? How do we approximate derivatives and integrals? And this is the last fundamental problem that we'll be examining this semester, and that is given a continuous function f of x, find a point that will refer to all chapter long as x star, such that f of x star is equal to 0. In other words, we're trying to find a root of f of x. Not necessarily all the roots. I mean, if you have a function that you believe has multiple roots, you can try whatever methods you have here. You can try applying them several times to find what the roots there are. But for now, we're focused on finding a root of a given function. Now, I mean, mathematics, you've all solved equations of various kinds ever since your algebra days. But the set of equations that the types of equations that you're able to solve, like on paper, is it's very narrow class of equations compared to types of equations that are out there. Here's some examples of equations that y'all should be able to solve, like a quadratic equation by factoring in or using a quadratic formula if necessary, or a trigonometric equation. So in this case, you can get a value for x, like an exact value for x. In this case, it would be like 60 degrees or pi over 3 radians. Plus periodicity, or you can use inverse cosine to get a solution. So these are perfectly fine, but it would be very easy to make a small change to equations like these to get something that you have no idea how to solve. For example, if I have the same polynomial but equal to e to the x instead of equal to 0. Or if I take cosine x equal to 1/2 and I multiply the left side by x. So trying to find a solution to x cosine x equals 1/2. Usually the equations that you can solve involve a very specific kind of function, like just polynomials or just trig functions or just exponential logarithmic functions or one or the other. Those kind of equations you can work with without too much difficulty much of the time. But when you have equations that mix different types of functions, it's game over algebraically. So we need another approach. So the kind of method that we're going to learn about 4 different methods in this chapter And all of them have in common that they will generate a sequence of iterates. They're all iterative in nature. So we'll obtain a sequence of values, x1, x2, and so forth, that hopefully will converge to an exact root of function f of x. So it's a convention when referring to a sequence of values generated by some iterative method to use this notation of superscripts and parentheses to refer to an iteration number. Now, I'm only going to talk about one such method today, and it's a bisection algorithm, which you might have heard about in calculus. But before getting to any methods, you can lay down some general concepts that apply to whatever root finding method you might have. First is order of convergence. Now, this is not exactly the same as rate of convergence that you saw before, back in chapter 2. So, if we have a situation where there's a common ratio of your latest iterate, xk plus 1, minus x star, so the error in the k plus first iterate, and some power of the previous iterate minus x star. So if there's a well-defined ratio of new error to old error raised to a power r, so these ratios converge to some constant c as k goes to infinity, then that power r is called the order of convergence, and it must be greater than or equal to 1. Now, certain values that will come up, methods that we'll look at, like r equals 1, so convergence is linear in that case. So that means that each error after k plus 1 iterations is approximately some fixed constant times the previous error. So in that case, a constant c needs to be less than 1. So for example, maybe c is 1/2, so each error is roughly half the previous error. So then you can be certain that if that's the case, the error is definitely going to 0. Because if c is greater than 1, that would allow the error to grow. We definitely don't want that. So first couple methods that we'll see have exhibit this linear convergence. If r is between 1 and 2, then we say convergence is superlinear. So that's a more rapid form of convergence. And then we'll also see an example of when r is equal to 2, convergence is quadratic. And then there could be cubic and quartic and so forth. But all the methods we'll see are either linear, superlinear, or quadratic. So we like quadratic. Like if the error is already small, and then the error in the next iterate is proportional to the previous error squared, that's going to be much smaller still. So the larger r is, the more rapidly your iterative method will converge to its limit. Alternative characterization of superlinear is if you show that r is equal to 1, but c is actually equal to 0, that's also a sign that the errors are going to 0 faster and faster, so that's also superlinear convergence. So there's two characterizations here. Questions so far? I know I've probably covered anything yet. Okay, Okay, the constant c, that is this limit, that's called the asymptotic error constant. Certainly it's going to be non-negative. So for some methods, we'll be able to figure out what that asymptotic error constant is. This ratio of errors. In the case of linear convergence, we actually do have a rate of convergence. So remember, rate of convergence, order convergence, not the same thing. And in this context, it's defined in terms of the asymptotic error constant. So it's minus log to the base 10 of capital C. So what it means in this case, and I will say again, this is distinct from the notion of rate of convergence in chapter 2, because mathematicians are independently coming up with terms that really are the same term, that mean totally different things in totally different contexts, and because that's just how we roll. So what does it mean in the case of linearly convergent root finding methods? It's how many decimal digits you get in each iteration. So what that would mean is whatever rho is equal to, the reciprocal of that is how many iterations you need to get a new digit. So let's suppose, for example, suppose c is equal to 1/10. So if c is equal to 1/10, that means the error is being reduced by a factor of 10 each iteration. So then if I plug c equal 1/10 into here, I'm going to get rho equal 1. That means you get one new decimal digit correct each iteration. Whereas if c was equal to 0.01, so 1/100th, then rho would be equal to 2. So you get 2 digits per iteration in that case. So only half an iteration is needed to get one new digit. So among methods that are linearly convergent, that's where the constant c becomes particularly important. Because let's suppose c is equal to 0.9. So c is fairly close to 1. That's a slowly convergent method. Deciding whether I want to try a different approach. Whereas if c is equal to a very small number, so not far away from 0, then linear convergence is still not the best, but linear convergence with a small c, the error is still going to 0 pretty quickly. So that's desirable. So in some cases, we might be modifying a linearly convergent method to improve the value of c, make it smaller. Okay. Now, still focusing on the general root finding problem, let's look at existence and uniqueness of a solution. Now, so there's one situation where you can confirm existence of a solution to f of x equals 0. This is from calculus 1, intermediate value theorem. So if you have a continuous function f on interval ab, and if f of a and f of b, so values of the endpoints, have opposite signs, then the continuity that guarantees that f has to be equal to 0 somewhere in between. So the first method we'll learn about, bisection, makes use of the intermediate value theorem, and the fact that it can guarantee a solution under certain circumstances. It's really the driving force behind that. Now, sometimes though, suppose you have a function that is greater than or equal to 0 everywhere. For example, the quantity x minus 1 squared. So that has a root at x equals 1. But the intermediate value theorem would never be able to help you confirm the existence of a root in any interval because the function never changes sign. Those are the worst kind of functions to deal with for root finding methods. Functions that don't change sign. And we'll see why as we go. As far as uniqueness, we don't have much to go on here. But we do have what's called the inverse function theorem. So what that says is if f has a root at a certain point x star, and if a derivative at that root is non-zero, then we can say that this equation, f of x equals y, is guaranteed to have a unique solution near x star as long as y is close enough to 0. So, so at least locally, we have uniqueness of a root. But it doesn't really give us very much, unfortunately. Okay. All right, now, very important though for numerical methods. If f at x star is 0, so x star is the root, and if the derivative is non-zero, so not only do we have like locally uniqueness, so we say that x star is a simple root. Those are the easiest roots to find numerically because of its local uniqueness. Whereas if a derivative at the root is also 0, then we say that f is degenerate at that point, and x star is a double root. Or if the second derivative is also 0, it's a triple root. So it's a root with multiplicity greater than 1. So for example, the monomial x to the n has a root of 0 and the multiplicity is n. So when f is degenerate, root finding methods don't work so well. At least the most rapidly convergent ones that we're seeing. They may show rapid convergence when you have a simple root, but if you try the same method where it's a double root or worse, then you lose that. You tend to lose that rapid convergence. So basically multiple roots are like the kryptonite of root finding methods. Okay. What else to say? Like for example, Newton's method that we'll see toward the end. When you have a simple root, it's quadratically convergent. R is equal to 2. If you have a multiple root, it becomes linearly convergent. So R changes to 1. So order convergence isn't even necessarily a property of the method. It's also dependent on the root itself. One more topic before I get into covering a specific method: sensitivity solutions. Very important for numerical methods. So I want to recall something from chapter 2. That if you're trying to solve a generic problem, y equals f of x. So x is your input, y is your output, f is whatever your algorithm is for the exact value. That the absolute condition number, so how sensitive the problem is to changes in the data, is estimated by the absolute value of the derivative at the input. So we're going to use that to measure the sensitivity of a problem finding a root of that. Because if you're trying to solve the equation f of x equals 0, basically what you're doing is you're solving this problem. That your output, which is your root x star, equals f inverse, and the input is 0. So the function you're trying to evaluate in this context is not f, it's an inverse of f. Now, we're assuming that an inverse exists. And at least if a derivative at the root is zero, if a derivative at the root is non-zero, the inverse locally does exist guaranteed by the inverse function theorem. So, if we want to know the condition number of this problem of finding the root of f, well, we need the derivative, but not of f. We need the derivative of f inverse. So a quick review of inverse functions. So if f is a one-to-one function, you remember a function has to pass what's called the vertical line test just to be a function. A vertical line can only pass through graph at most once. If f is one-to-one, that happens if and only if the graph also passes the horizontal line test. So in that case, it has an inverse. So the way to find the inverse function is, so y equals f of x is equivalent to x equals f inverse of y. So as an example, here's my f of x, so squared vector of minus 1. So what I can do is I can take this equation, y equals squared vector of minus 1, and solve it for x. And I get this, my inverse function, x is square root of y squared plus 1. I may be careful about the domain. Like in this case, this function is only defined if x is greater or equal to 1 in absolute value. Here, the range of this function, if we assume a positive square root, is y greater or equal to 0. So then, for the inverse function, the domain and range will switch places. I think it's supposed to be covered in calculus, but I'm not sure if it is.
Are we gonna do a diary today?
No, we're not.
It's covered in at least college algebra course.
Oh, yeah, I've heard about that. Okay. Yeah, it's at UC Irvine, I covered it in calculus 2 of all places. Right before covering the exponential logarithmic functions because they're inverses. Yeah. So, but it's never been on the syllabus of a calculus class here. I taught all 4 calculus classes, but
Maybe it's because it's in the college algebra.
yikes, okay. So I'll just assume everybody's forgotten it. This is like in general, yeah. Okay. Now, a function and its inverse satisfy these relationships that they cancel each other out. So f of f inverse of x is just x. Similarly, f inverse of f is equal to x. And I can use the first one of these equations to get a hold of a derivative of f inverse. So if I take the derivative of this equation with respect to x, both sides. So on the right side, of course, I get 1. On the left side, I have to apply the chain rule. So I'll have f prime of f inverse of x times the derivative of f inverse, and all of that is equal to 1. So now I can rearrange this, and I have this differentiation rule for the inverse function. So notice f inverse prime is equal to 1 over f prime. And that makes perfect sense because what is a derivative? It's a rate of change, dy over dx. When you go to the inverse function, x and y switch places. That fraction flips. So intuitively, it's not surprising that we would have a rule like this. So what does this mean for root finding? We're trying to find this root of f, so x star f inverse of 0. So what we're doing here is the condition number of this problem, the absolute condition number, is the derivative of f inverse at 0, but that's going to be 1 over absolute value of f prime at the root. So what does this mean? How do we interpret this? That means if a graph of f is roughly flat near x star, which means the derivative is very small, then the problem is ill-conditioned. Whereas if the graph of f is very steep at the root, then the problem is well-conditioned. Now, I'm going to take this opportunity to recall backward error analysis. The approximate solution, which we'll call x hat, which is our approximation of x star, is the quote exact solution of a nearby problem. So x hat is f inverse of some value epsilon that hopefully is near 0. So, but that would mean that f at x star is epsilon just by rearranging this equation. So what does that mean? That so if a derivative is very small near the root, then what that would mean is epsilon might be small, but x hat might be nowhere near x star. So this is a consequence of the problem being ill-conditioned, that your forward error is large, even though your backward error is small. Because remember, backward error times condition number is forward error. And I think I have an example, yeah, I can show you of ill-conditioned versus well-conditioned. I should have it in here somewhere. I do. Okay, so here's an example of a problem of finding the root of f of x where that is well conditioned. So the graph of that is pretty steep at the root. Y is changing rapidly with respect to x. So let's suppose right here that this circle also on the x-axis, but to the right of the root. Suppose that was my computed root. So it's an approximation to a true root. Now, here the backward error is actually fairly large. My approximate solution is equal to f inverse of epsilon, where epsilon is large. But because the problem is well conditioned, that even though the backward error is large, the forward error is small, and that's a preferable situation. Whereas here, in the ill-conditioned case, the derivative is actually equal to 0 at the root. And what's happening in this case is I could be so here's a situation where my backward error is again not very small, and my forward error is ginormous. Because you're taking that backward error, multiplying it by the large condition number, and getting this forward error. Because when you are when you're computing iterates, the approximate roots, it makes sense to check your roots by plugging them into f. And are you getting something close to 0? So what could happen in a situation like this is I could be generating an iterative, say around here. I could plug it into f, and it tells me, oh, your value with f at this point is pretty small. You're close to a root. Well, actually, you're not. So plugging an approximate root into f and checking for a small value is deceiving when f is ill-conditioned. Whereas if it's well-conditioned, if you plug an x value into your function and you get a small y value, then you can trust you actually are near the root. So that's the ramification of a well-conditioned versus ill-conditioned problem, is that you can, when you're trying to check roots by plugging them into f, it's more reliable in a well-conditioned case. Any questions about this conditioning? What it means? All right, now talk about first of four methods that we'll see in this chapter, bisection. So here's a general idea behind bisection. So the situation is this: we have some function f, we know it's continuous on some interval ab, and it's given that f of a and f of b have opposite signs. So your starting point is not just a given function, but you have an interval to work with. And f is known to change sign on the interval. And we need that for bisection to be used. What you can do is you can try plugging in points and see if you can find at least one value point where f is positive and one where f is negative. So then you apply the intermediate value theorem. So you know that f is equal to 0 at some point in between. But the intermediate value theorem is an existence result. It tells me that that point C exists. It doesn't give you any clue where to find it. And then they assign these foolish problems in Cal 1 classes where they find the point C. It's like, no, it's not what it's for. Okay. So here's what you do. You compute the midpoint of the interval AB. So m is equal to a plus b over 2. And then you compute f of m. Now, if f of m itself happens to be 0, then it's Miller time. You're done. But so let's assume that it's not, that we're not that lucky. Well, f of a and f of b have opposite signs. So f of m has to be a different sign from one of the two. So, so here are two things that can happen. So f of m might have the opposite sign as f of a. So you apply the intermediate value theorem again. So I'll make that clear here. Apply the intermediate value theorem. There has to be a root between a and m. The only other possibility is that f of m and f of b have opposite signs. One of these two has to happen if f of m is non-zero. So in that case, again by the intermediate value theorem, the root has to exist between m and b. So in other words, you've cut your search space in half just by evaluating f at one point, the midpoint. So that's how bisection works. You are repeatedly bisecting your interval. You start with AB and then you cut that in half using m, then you compute the midpoint of that smaller interval. So you're always narrowing it down. So the maximum possible error is reduced by a factor of 2 every single iteration. So one thing that we can say about this method, it is reliable. So if you have an interval AB to start with, where f is known to change sign, then this method absolutely will find a root eventually. Cutting the error in half, that's not great. We can definitely do better than that. So the reliability is nice, which is one reason why bisection is actually used in practice, often in conjunction with other methods. So what we can say in this case, since the error is reduced by a factor of 2, we can say that there's linear convergence. So r is equal to 1 is the order of convergence. And then the asymptotic error constant, capital C, would be 1/2. So all you gotta do is find a method that is either linearly convergent with a smaller c, or is has a higher order of convergence. like a superlinear quadratic, and you got this method B. Okay. So to get an idea, like let's suppose you're starting on the interval, say 0 to 1. Then, if you're so since the error is cut by a factor of 2 every iteration, what that means is you're gaining one additional binary digit of accuracy every iteration. But if you're using IEEE double precision floating point arithmetic to get full precision, that means it would take 52 iterations. We'll see methods that can converge in a lot fewer iterations than that. Actually, you already have seen one from homework 1, the Newton square root problem. It was sort of in disguise. So when we get to that topic, I'll revisit that. All right. So what I'm going to do now is show you an example of bisection in action. There are a couple of examples. So here, for example, we have a function is x minus cosine of x. And we're working on the interval from 0 to pi over 2. So when x is equal to 0, the value of f is minus 1. Because cosine of 0 is equal to 1. And then at x equal pi over 2, then the function is equal to pi over 2. So we have a sign change. We know there's a root in here somewhere. So here a function value is negative. Over here it's positive. So we compute the midpoint, which is pi over 4. We evaluate the function there. We see that it's positive. So the sign here is the opposite of the sign over here at x equals 0. That's kind of cool. When I swirl this around, then I get a big ass arrow. Scary. So now I know there has to be a root between here and 0 and pi over 4. So then I can compute the midpoint in here and keep looking. And what happens when you do that? Okay, so more iterations are carried over here. So here, pi over 4 is my first midpoint. Here's my second one at pi over 8. And the value is negative, whereas the pi over 4 is positive. So somewhere between pi over 8 and pi over 4, there's a root. So then I consider this point, which would be 3 pi over 16. Again, the function value is negative, so now it's narrowed down between here and here. So now I get this point, which would be like 7 pi over 32, and so on. And I keep getting closer and closer to where the graph crosses the x-axis. Okay. So any questions about the visual of bisection? It's not very sophisticated about it. I have another example here. Okay, polynomial x squared minus x minus 1. So if I substitute x equal to 1, I get minus 1. And if I plug in x equal to 2, I get 1. And it's polynomial, so it's certainly continuous. So by the intermediate value theorem, there has to be a root somewhere between x equals 1 and x equals 2. And I have a table here that shows what happens. So at the outset, my interval is from 1 to 2. So then I remember at 1 it's negative, at 2 it's positive. So then I compute the midpoint, 1.5. Well, adding my function, I get a negative value. So that means, and the function is positive at x equals 2. So between 1.5 and 2, that's my next interval. So with each iteration, you see the interval is getting smaller and smaller. If we focus on the midpoints, notice that they are kind of sort of converging. like 1.618. And notice at each of these midpoints, I plug them into a function. Since the midpoints are converging to something, presumably a root of f, the function values ought to be getting smaller, and we see that they are, but slowly. So here I've carried out 10 iterations so far, computed 10 midpoints, and I only have like a few decimal places of the root, 1.618. And I was going to ask y'all, hey, what is that number? But that's written right here. So, never mind. Okay. So in fact, one of our own students, Chandler Jim, for her master's thesis, implemented an algorithm that uses a combination of bisection and a method that we'll see later that converges more rapidly called the CCAT method. So the idea is first find an interval where there is a root, and then actually try the CCAT method on it, which because it converges more rapidly, and we'll learn about that later. But if a CCAT method produces an iterative that is outside the interval, we reject it, and then perform one iteration of bisection, just to narrow things down a little bit, then try CCAT method again. So that would be faster than just using, it's faster than using bisection all the time, and it's more reliable than using CCAT method all the time. That's an example of what's called a, yes, Michelle will know something about CCAT method as well. So that's an example of what's called a safeguarded method, when you're trying to get the best of both worlds, a reliability of a method like bisection and a rapid convergence of a method like CCAT method. Another thing I want to show you is here's some pseudocode for the actual algorithm for bisection. And I believe this is one of the homework problems that I assigned for this section to implement that in MATLAB. So at least for the pseudocode, you're well on your way to having a MATLAB function, basically getting this in the MATLAB syntax. So you can have a loop. It can be a for loop or a while loop to keep iterating until you get convergence. And for bisection, you're guaranteed to get convergence. So you go ahead and compute the midpoint and check. What if you got lucky? What if the midpoint actually is a root? Okay, then you should certainly stop. Otherwise, any point in the interval AB, if you know that a root exists inside that interval, then literally any point in the interval AB is at most b minus a over 2. Oh, wait. I was about to say something totally wrong. Let me back up a bit. Okay. If you know that there's a root inside the interval AB, then the midpoint has to be within b minus a over 2 of that root. So if you think of the midpoint as your iterate, then you can reliably say that the error in M is at most b minus a over 2. So that's why I have this condition in the if statement. If b minus a over 2 is less than some tolerance, it might be the absolute error, the maximum absolute error of that one, then I might as well stop and say that my value of x star is the midpoint. So that's my output. Okay. Now, if I've not converged, then I continue the bisection. So I check does do FA and FMM have opposite signs? So one way to check is by multiplying, because I don't care which one is positive and which one is negative. I just care whether they have opposite signs or same sign. So if their product is negative, then I would change my right endpoint to be the midpoint. So now I'm working on the interval a through m, which is now new AB. Otherwise, if this product is not negative, then f of m, f of b must be negative. So then I change the left endpoint of my interval in which I search. And then the iteration will continue, eventually converging to a loop. Although, in terms of how various operations, like arithmetic operations, logical operations, are implemented in hardware, actually, what I'm wondering is it less efficient to compute this because that involves the multiplication and floating point multiplications are among the more expensive arithmetic operations compared to addition and subtraction. The alternative would be to compare, like, is f of a less than 0 and f of m greater than 0, or f of a greater than 0, f of m less than 0. But that's a compound condition. That's a lot of logical operations to employ. I'm not really sure which one is faster, to be honest. I guess I can find out now to find out. But again, both approaches would be so fast. It'd be hard to check my timing and mallet. I'm sure someone's looked into this. But often I see in American analysis books, it's written this way, I guess because it's mathematically elegant. It's one thing to check. Okay. Actually, reminds me of something I wanted to point out from, I didn't mention when I covered it, in Romberg integration and interpolation I covered last week. I'll make sure I'm looking at the right thing. Oh, went to the wrong section. Okay. When I described okay. Oh, you know what? I don't have it here in the book. It's in the notes. Okay. When I first described Richardson extrapolation, I wrote the formula this way for the new value. But then, when it came to actually, it is why I carried out an example. But then, for Romberg integration, it was written a little differently. Volume was slow. It was written like this, where the new value is equal to a previous value, and then this fraction. And this way of writing it is better because it involves one more addition, but one less multiplication. Multiplication is more expensive to carry on the hardware than addition. So in other words, multiplication and division both are more expensive than addition or subtraction. So this way of writing the formula is more efficient. So just little things like that. When computers are performing gazillions of operations, you find one little tweak that can make things faster. It can add up to a big difference. And a lot of researchers and programmers, they spend a significant amount of time on this to make things as optimal as possible. Why is this zoomed out so much? Okay. Sorry, I digress, which I often do, I know. Okay, there's a theorem about bisection. About how rapidly it converges. So the error after k iterations is at most b minus a over 2 to k. Where the iterates are considered to be the midpoints. So that goes with what I was saying earlier, that with each, if you're consistently updating interval AB in the algorithm, like the algorithm I showed you, then the error is at most b minus a over 2. But that's with the current AB when you keep changing a and b as your interval gets smaller and smaller. This is with regard to the original interval AB. After k iterations, your error is at most this. And one of the homework problems from this section is to prove that. And this is where you keep in mind that you can drop the most two assignments. Okay. Actually, which problems did I assign from this section? Oh, 2, 3, and 5. Okay, so not this one, which is good because I gave the answer away earlier. But yeah, what? Yeah, I actually mentioned what the answer to this was. 52 iterations.
52 iterations.
Because that's the amount of that's the number of the digits that your Ventissa has.
Is this on one of our homework assignments?
This one is not. This one is to prove this theorem. Up here, and then okay, there's one MATLAB problem to implement the bisection algorithm that's given up here. And then the other problem I assigned. Oh, this one. Here we have a polynomial that has 2 real roots. Now, bisection is only going to find 1 root. So you might choose an interval AB where a function has multiple roots, but bisection will still only find 1 of them. Okay. But here it asks you to find 2 disjoint intervals that you can use to find the positive and negative roots. And then why use those instead of one larger interval? So that's what's assigned for explorations for this section. And I think I assigned something from 10.1 that's about root finding in general. List 3 functions where that's what I assigned? Yes. That has no roots, 1 root, or multiple roots. So all kinds of possible answers for that one. Have fun. Okay. Wow, I'm surprised I used most of the last time. But it's like round off of the month, I'm not going to digress. Okay, so are any questions about root finding in general or bisection? All more questions? And finally, fix the schedule to make clear that there is no class next Tuesday, the 21st. I'll be off for Thanksgiving by then, and maybe some of you will be too. Okay, so we'll see a better root finding method on Thursday.